Part A, show that the point P, 1, 0 lies on the curve. So the x-coordinate is 1, the y-coordinate is 0. So if I substitute 1 in here instead of x, so when x is 1, substitute the 1 in instead of x, ln 1 is just 0, sine of 0 is 0. So I have shown that when x is 1, y is 0. So therefore the point 1, 0 lies on the curve. This is 1, 0 here. Part A, done. Part B, we have to find the coordinates of point Q. Point Q was a maximum point. So I know at that point the gradient is equal to 0. At this point here, that's a maximum. The gradient is 0 at a maximum. So I'm going to differentiate very carefully, because I'm going to need to use the chain rule for this, because I've got the ln x inside the sine function. So we're going to differentiate the outside function first. So differentiate the sine, and I get cos. Inside stays the same, so the ln x stays inside there. That doesn't change. So I've differentiated the outside function, and now I need to multiply that by the derivative of the inside. The derivative of ln x is 1 over x. So my gradient function is cos ln x multiplied by 1 over x, which I could write like that. And that needs to equal 0 at a maximum point. I'm then going to multiply both sides by x, so I get cos ln x is equal to 0. If I now do cos inverse to remove this, and I'll do cos inverse of 0, cos inverse of 0 is pi over 2. I will now do e to the power on both sides to remove the logarithm, and I find that x is e to the power of pi over 2. So that's the x-coordinate of point Q. For the y-coordinate, we can substitute that back into the original equation. So if I substitute that e to the pi over 2 here, which is what I've got over here, ln of e to the pi over 2, or the ln e will cancel out and I'll just get pi over 2. Sine pi over 2 is 1. So we know the y-coordinate of point Q is 1. So that's part B, done. Part C. Now, this was a 9-mark question. It's a long process and it's a difficult process. The overall strategy for part C, we're working out the shaded area. So what I'm going to do is I'm going to integrate the curve from P, which is 1, to Q, which is e to the pi over 2. So if I integrate between those, that's going to tell me all of this area here. And then what I'll do is I will subtract the triangle from that, and that will leave me with just the shaded area. So that's my strategy. So down here is the integral from 1 to e to the pi over 2 of sine ln x with respect to x. Now this is a very complicated function to integrate, so I'm looking at that and I'm thinking, what's the most complicated thing about this? It's the fact that I've got an ln x inside the sine function. So I'm thinking if I made a substitution here, that might make it simpler. If I could change this ln x to just be u, then I would just have sine u, which would be simpler, hopefully. So That's why I'm thinking about this substitution here. I'm saying let u be ln x. As usual, when we do integration by substitution, the first step is to differentiate my substitution. So I'm differentiating u with respect to x, differentiating ln, that gives me 1 over x. I've then made dx the subject, so I've multiplied by x over here, and I've multiplied by dx over here, and that's given me that dx is equal to x du. Now I'm thinking about what x is in the u world, so I'm just going to rearrange this. So if I do e to the power on both sides, I'll get e to the power u is equal to x. E to the power u, the e and the ln cancel out, so that's why I get that x is e to the power u, which is what allowed me to make that change there. So this will get plugged into here. This we know is a u now. Now we just need to deal with the limits and change those limits to be in the u world as well. So that was my next step. So my lower limit was when x was 1. So when x is 1, substitute 1 into my substitution. Remember the substitution was u equals ln x. So if I put 1 there instead of the x, I get ln 1, which is 0. The upper limit was when x was e to the pi over 2. So when I substitute that in, I get ln of e to the pi over 2, which is just pi over 2. So that's my upper limit. Done. So lower limit, upper limit. So therefore, my integral has been turned into this integral here, the integral from my lower limit of 0 up to the upper limit of pi over 2 of sine u e to the power u du. Now, unfortunately, this is a very difficult integral to do. I can see that it's a product of two functions. It's a product of sine u and e to the power u. Because it's a product, I'm thinking that I could do integration by parts on it. The problem with this, as we're going to see, is that when we do integration by parts on this, it doesn't turn out nicely. Let's go to the next slide. So, first thing to notice, I have swapped the u to be a w here. Just swap. The only reason I've changed that to be a different letter is because when I do integration by parts, I know I always have a u and a v dash. And I don't want to get confused between the u that was in my original question. Remember, to begin with, this was a u, this was a u, this was a u on the other page. And I don't want to get confused between that u and this u. So that is why I've just swapped that u to be a w in the original question. It doesn't matter, it won't change the results. I'm just swapping it for a different letter. Right, so I've selected the u to be e to the power w, and I've selected my v dash to be the sine w. So this is my u, and this is my v dash. Differentiating the e to the power w will be e to the power w. Integrating the sine w will be minus cos w. And now I'm applying the biparts formula. The biparts formula, u times v minus the integral of u dash times v. Right, what I'm going to do now is I'm noticing that I've got a minus and a minus here, so I can turn that into a positive. So let's turn that into a positive. Let's get rid of that completely and turn that into a positive there. And right, we're going to use by parts again now. So I'm going to let this e to the power w be my u, and I'm going to let this cos w be my v dash. Differentiating the e to the power w gives e to the power w. Integrating the cos w gives sine w. So, on this next line, I've got the original question, which is this here. I've just copied this part down to here. And then everything in this bracket here is the result of doing integration by parts here. So I've got the u times v minus the integral of u dash times v. Now, I'm adding the e to the power w sine w, which is just here. And then I've got this minus e to the power w sine, minus the integral of e to the power w sine w. Now what I noticed is that's the same thing as what I started with over here. So what I'm thinking here is if I could add the integral of e to the power w sine w dw to both sides here, so I'm adding that integral to both sides of this equation. So on the left hand side I've got two lots of that integral, so that's what this here is. And on the right hand side, well, these have cancelled out now, these have disappeared. And so the right hand side is just all of this, which has already been integrated. So all of this working out has allowed me to say that two lots of the integral is equal to this. So therefore, if I divide both sides by 2, one lot of the integral is half of this. So half, half. And there we go, I've finished that integral. So that's allowed me to say that the integral of e to the power u sine u, I can change these back now, e to the power u sine u du is equal to a half e to the power u cos u plus a half e to the power u sine u. And I'm now going to put my limits in. Remember, the upper limit was pi over 2, the lower limit was 0. So substituting the pi over 2 in here, 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 and here, first of all, that gives this. Then I'll do the same thing with the 0. That gives this. Just going along and simplifying each of these terms then, the cos pi over 2, that is 0. So that first term's going to just disappear completely. The next term, the sine pi over 2, is 1. So I get a half e to the power pi over 2 times 1. So I've got that answer here. The cos 0 here is 1. So that gives me minus a half times 1 times 1. which is minus a half, which when combined together with the negative here, the minus minus a half, will become a plus 1/2. So that's where that there comes from. The sine 0 here is just 0, so that term disappears completely. So all of this calculation, all of these calculations on this page allows me to say that the area underneath that curve is a half e to the pi over 2 plus 1/2. So that is what allowed me to say that on the other page. So I've worked out so far that the area underneath the curve between those two limits, I've worked out that all of this, all of that is the half e to the pi over 2 plus a half. I'm now going to take away that triangle. I don't want to include this triangle here. So I've just drawn a rough sketch of the triangle over here with the coordinates of P and Q marked on. So the area of that right angle triangle there, half base times height. The base of that triangle, considering that I know that the x coordinate here is 1 and the x coordinate here was e to the pi over 2, the base of the triangle there is e to the pi over 2 minus 1. The height of the triangle is just 1. So half base times height, half of the base times by the height. So half of e to the pi over 2 is half e to the pi over 2. Half of the minus 1 is minus a half. So my area underneath the curve, remember, was this. The area underneath the triangle was this. And so if I take those away from one another, the half e to the pi over 2 minus the half e to the pi over 2, they've disappeared, they've cancelled out. The half minus the minus 1/2, so a half plus 1/2 is 1. And that is the shaded area. After all of that work, all of those 9 marks, the answer is 1.